Hello, welcome back to Learn Physics. In today's topic, we are continuing with the kinetic theory. Okay, in last class we learned about the specific heat capacity of monoatomic, diatomic and polyatomic molecule or polyatomic gases. That one we learned, isn't it? And along with that, equipartition of energy, Dalton's law of partial pressure, all those things we learned. And today we are going to study about specific heat capacity of solids and liquids. In liquids I am considering water. Okay, first we will consider specific heat capacity of first one solid. First we will consider solid. Okay, so what is the degree of freedom of a solid? So while considering the specific heat capacity, as we considered in the last video, first we should consider about the degree of freedom, isn't it? It will be having 3 degrees of freedom in a solid. Okay, 3-dimensional way it can move. Okay, and in the solid, see, it is very closely packed. The atoms are very closely packed. Since it is very closely packed and it is very near to it, see, the vibration, it can move, it can oscillate there, it can vibrate there. So vibrational degree of freedom, what will be the total energy of a vibrational degree of freedom? As I told you in the previous video, it will be having both potential energy and kinetic energy. So we will consider the total energy as 2 into half kBt. Rest everything we will consider it as half kBt only. Each one will be having energy, each mode will be having energy half kBt. But only in the case of vibrational degree of freedom, we will consider 2 into half kBt. Okay, 2 into half kBt will be the energy of one molecule, one atom. So it will be kB into T. So this will be the energy of one atom. Okay, so this is for one-dimensional way. If it is moving 3-dimensionally, so energy will be considered as energy equals 3 kBt. Okay, if I am considering 1 mole of solid, if I am considering 1 mole means it will be having how many number of atoms? Avogadro number of atoms will be there. So Avogadro number of atoms. Number of 1 mole of solid consists of Avogadro number of atoms. Okay, so it will be having Avogadro. So what will be the total energy? Total energy of 1 mole of solid, if I am considering, it will be having 3 Na kBt in 3-dimensional way. Okay, so 3 into kB into Na into T. So what is this Na into kB? Remembering? Yes, R, universal gas constant, is R, 3RT. Now how we will find out the specific heat capacity? Delta Q divided by delta U divided by total internal energy divided by time, dou U by dou T. So we will get it as delta by delta T into 3RT. So it will be equal to 3R. This is the specific heat capacity of a solid, which is for 1 mole of solid, if I am considering 3R. So it will be a constant. 3 is a constant, R is also a constant. So specific heat capacity of solids will always remain constant. Okay, in a 3-dimensional way. Okay, next we are going to consider about the specific heat capacity of water. So if I am considering water, it will be having, see, the same way it will be having vibrational degree of freedom, and so it will be, the total energy will be kBt, it will be total energy energy equals 2 into half kBT. So it is kB into T in 3-dimensionally. While we are considering, it will be the total energy will be equal to, for one atom I am considering 3 into kBT. But we know water will be existing as a molecule, isn't it? It will be having 2 hydrogen and 1 oxygen atom will be there. 2 hydrogen atom, H2O. So 2 hydrogen and 1 oxygen. So how many atoms are there in a one molecule? One molecule, it has 3 atoms are there. So what will be the total energy of a water molecule if I am considering? Total energy of water molecule. Water molecule will be equal to 3 into, because 3 atoms are there. For one atom it is 3 kBT total energy. So what will be the total energy of a water molecule? 9 kBT. So while we are considering the specific heat capacity, that is C is equal to delta Q divided by delta T, or delta U by delta T, we will get, therefore it is equal to 9 kB into Na for 1 mole of water. If I am considering 1 mole of water, we will be having, for 1 mole of water, it is 3 kB into Na. What is that value? 9 into R, universal gas constant. Okay, so 9 into that, also a constant. Okay, specific heat capacity of water which I am considering, it will be, we will be taking in this manner. Why this 9 is coming? Because it has 3 atoms, 2 hydrogen and 1 oxygen. 3 atoms are there, so we can consider it as 3 into 3 kB into T, that is 9 kBT. For 1 mole of a gas, it will be having Avogadro number of atoms, so it will be 9 into R. Okay, it is a constant. So this is, water is a simple molecule. While we are considering there's liquids, in that water is a simple molecule, isn't it? It has only 3 atoms. But when we are considering this alcohol, methane, although the methane is a gas. So alcohol and while we are considering, it is also a liquid state, isn't it? So all other molecules, some other molecules while we are considering, which is complicated, more number of atoms are there, means their degree of freedom is very difficult to predict. Okay, so while we are considering this simple molecule, we can accommodate this classical mechanics. So these degree of freedom and this equipartition of energy, all those things we explained on the basis of classical physics. Okay, so this classical physics is enough to explain the simple molecule. But while we are going into a higher level of molecules, this classical mechanics won't work out. Why? Because their degree of freedom will be changing, since it has more number of molecules, and collision, vibration, everything will be increasing over there. Okay, so it is a barrier there. Okay, so in those cases, instead of classical mechanics, we should use quantum mechanics. Okay, quantum means we will be considering again in smaller amounts. Okay, we will be considered, that is quantum mechanics. That is one of the limitations of this degree of freedom, the explanation of degree of freedom by using a classical mechanics. And we know, see, the specific heat capacity is a constant here for a solid as well as in water it is constant. That means at any cause it won't change, isn't it? That is, as per classical physics, it won't be changing. But we know, see, if I am taking water and freezing it 0 degrees Celsius, then its degree of freedom again it is changing over there, isn't it? So because it is coming to this water, or it's very freezed over there, it can't move that much, isn't it? Again more constraints are coming, that means degree of freedom is again changing. Okay, but using this classical mechanics, we got it as, it is 9R, it is not changing. but as temperature decreases, degree of freedom also will be decreasing. In the practically while we are considering, degree of freedom also decreasing, but that explanation is not coming under classical physics. So that is another drawback of this classical mechanics. So while explaining, so that is the reason we now the quantum mechanics has more importance. Why? Because using classical mechanics many things we can't explain, but while we are using quantum mechanics, that and all very easily we can, that and all we will study when you are coming to the higher classes. Okay, now this much it is clear for you. So what is the limitation of classical mechanics in using this degree of freedom also you understood, right? So here it is a constant, but at a low temperature it will be changing. That can't explain using this classical mechanics. And another one is, while coming to the higher molecules, higher level of molecules, this classical mechanics we can't explain properly. By using classical mechanics, specific heat capacity can't explain properly. Why? Because it is changing. The number of degree of freedom will be changing over there. While we are considering higher number of or large number of atoms in one molecule itself, then the degree of freedom also will be changing. These are the limitations of explaining with the classical mechanics. Okay, while explaining with classical mechanics, these are some of the limitations. Okay, clear? So next we are going to study about the mean free path and its derivation. Okay, next is mean free path. So mean free path. See, what is meant by this mean free path? See, what is meant by this mean free path? This one mainly we are considering about the gases. Okay, so suppose while if mama is preparing something in the kitchen, so when she is putting masalas or something, that time itself you won't get the smell, isn't it? It will take little bit time to reach to you who are sitting there in your study room. Mama is making something. It will take some time. See, gases are very free to move. Then why it is taking some time to reach to us? Okay, it is taking little bit of time, or in between some leakages there in the gas cylinder, kitchen gas cylinder, if some leakages there, it will take some time to reach to us. All of a sudden it won't come. It should travel from here to there. That is obviously it is there, but it can very freely move, right? Then why it is taking some little bit more time to reach to us, or to some distance, to cover some distance? Why it is taking some time? The reason is, see, the gas molecules will be of small in size. Their size is very small, and it is very small, mass also very small only, and since their size is very small, and when they are moving in between the molecules or in between the gas molecules, it will collide also. Because of this collision, its path will be, instead of moving in a straight line path, it will be deviating from their straight line path. Okay, that is the reason it won't be all of a sudden it won't be reaching to us. If we are straight to that also, the molecules won't be moving in a straight path. Why? Because in between collisions are happening and it will be deviating from their path. Okay, that is so what is the minimum distance required by the gas molecule to move without collision? What is the without colliding, how much minimum distance it is required? That is called a mean free path. Okay, so here we are going to study about what is the minimum distance required. Okay, for that I am considering a gas molecule which is having a diameter of d. Okay, so here another gas molecule is here. Here I am considering another gas molecule. All are having the same d. This also d. So what will be the minimum distance required to cover this? Say minimum d distance if they have, then without collision it can move, isn't it? So that is, if I am considering a volume here, okay, I am considering this is the center part of this and it needs minimum distance of d as required. Okay, so if v is the average velocity of the molecule in a time interval delta t, using in delta t how much distance it would have covered? Distance covered by an gas molecule as average velocity into time. This is the distance covered. Okay, so how we can find out, see what will be the minimum volume covered by the molecule? Volume covered will be volume covered by the molecule is area into distance covered. What will be the area? This much distance. This is the volume of this cylindrical column. This much of volume is required minimum. So pi d square, area into distance covered. This will be the minimum number volume covered by the molecule. If there are n number of molecules per unit volume, n is the number of molecules per unit volume. So the total number of molecules in the given volume, what will be the total number of molecules? This n is the number of molecules per unit volume. Then how many number of molecules in this volume? N into pi d square into average velocity into delta time. Okay, what will be the rate? N pi d square v by delta t. The rate means in 1 second. In 1 second, how many number of molecules will be covering this volume? This n pi d square v. Okay, so in 1 second, this many collisions are happening. For one collision, what will be the time required? 1 by n pi d square v. Okay, so for 1 second, the collision number of collisions are this much. Then for one collision, how long it will take? It will be taking 1 by n pi d square v. So time required for one collision, is one collision equals 1 by n pi d square v. Okay, so here we are considering about v, time required for one collision. So here we got it as for one collision 1 by n pi d square average velocity. Okay, so what is the mean free path which I told? Mean free path is the distance covered, the minimum distance covered by the molecule to travel without collision. For one collision, the time required is this much. So what will be the distance covered? Distance covered, minimum distance for between two successive collisions. Minimum distance between two successive collision. How we can find out? Velocity into time, isn't it? What is the time required for one collision? It is equal to v into 1 by n pi d square into average velocity. So we are getting it as n pi d square. So the distance between two successive collisions depends on the distance. Okay, distance between the molecules. Okay, it is depending on the number density. As the number density of molecules is increasing, this what will happen? Mean free path also will decrease. Okay, and it is depending on the size of the molecule also. As size increases, what will happen? Mean free path also will be decreasing. Okay, so it is depending on it is depending inversely on the number density and the size of the molecule. Okay, so I hope it is clear for you, and in next video we will be doing some of the numericals based on this chapter, and afterwards I will start the chapter oscillation. Okay, so if you like the channel, please don't forget to subscribe. Thank you for watching. Bye.